Hello everyone, welcome back to the Subscribe blog. Change of scenery. The previous episodes were mostly all interviews that I did in Redmond when I was there for my bi-monthly visits. Today I'm back in my studio at home here in Germany, and today I want to talk about starting to talk about something that is around things. Because we see a lot of customers for Service Bus and the Windows Azure platform in general starting to put general purpose computing devices, special purpose computing devices onto Windows Azure, start to connect them to Windows Azure, and are looking for guidance for how to do that. And we also see a lot of potential use cases, scenarios that we kind of see around several industries where a bit of cloud would help folks solving their problems a little bit better. So let me go and talk about this, because I was confused in the beginning, this general versus special computing device difference. This is obviously a general computing device. It's a notebook. It's a Lenovo X1 Carbon. And that thing is very good because it allows me to do all kinds of interesting things. It runs apps, it runs desktop apps, it runs those touch apps, how we call this, Windows Store style applications. But it's something that kind of helps me being informed. It can do all kinds of things. It could be a DJ, mix desk. It could be an information browser, and it can also go and compute all kinds of things for me. So these things, and servers and smartphones and tablets, are general purpose computing devices, primarily geared towards interaction with people, and they're kind of like a blank canvas that you can go and use to interact with people. Contrast that with contextual devices, things that are useful, that have electronics in them because there's a primary purpose that has nothing to do with computers, and where electronics, where computers, where logic, it kind of enhances that experience. I have one of those examples here. Look at that wonderful WinFlex. That is a model of a Boeing 787. Obviously the first purpose. I'm also a big fan of Airbus. Trying to endorse Boeing in any particular way, but I just picked that model up from my collection. That has a special purpose, right? It is the purpose of this thing is not to inform me. It is actually get me from A to B. The same is true for vehicles, cars, trucks, trains. There's a primary purpose which is rooted in the physical world and helps me to do things or to accomplish things which are physical and which are not about information. These things are all about information. These things are about making things happen in the physical world. So here's another thing that makes something happen in the physical world. It's a toaster, and the primary purpose of that thing is obviously not to give me information, but it is to make my morning bread wonderful and crispy, and that's a lamp, and that lamp's primary purpose is to give me light. And here I have a microphone. The primary purpose of that thing is to record my voice as I talk to you. And obviously here's also a special purpose device that is a coffee mug that is now empty. So there are general purpose computing devices, there are special purpose devices, and those special purpose devices sometimes are enhanced with electronics. There's some extremes, like if you take a look at this, the 787 Dreamliner, that is obviously a flying data center because it has a lot of subsystems, the avionics obviously, but also things like the in-seat entertainment system. So that has a lot of computing powers, a lot of computers in there, but all for general purposes. Not that you get something that you can go and program freely. You can't load your programs onto the in-flight entertainment system. It's all special purpose built. If we think about what people are doing with are looking for with computerizing these special purpose devices, they're looking very much for the same things that we're looking for when we think about those general purpose applications. So you make a website for to be run mostly on a mobile device or a desktop, or you write an application that's running on the desktop or that runs on one of those devices. One of the most interesting things you can do if you're building a very modern app is to figure out how your users are using it. So are you successful? So people are instrumenting their websites, they're instrumenting their applications to understand how people are using their apps so they can go and make their apps better. And it's actually fairly legitimate for a manufacturer of a thing, and even if it's as stupid as a thing as a toaster is, because the toaster is not a particularly smart device, it's just effectively what it does is it goes and takes electricity and turns that electricity fairly immediately into heat with a bit of a way to go and control that functionality, but it's otherwise it's not doing anything, and not anything particularly more interesting. But manufacturers of devices, even of that level of intelligence as a toaster, or the level of intelligence of a lamp, are looking to improve those devices. And the higher you go up in the value chain, the higher value those devices become. Right? This is probably a €20 toaster, probably to make a manufacturer this device. I don't even know what that costs, but it's probably going to make my wallet bleed, how much of a margin there might be. So it's actually legitimate for just as legitimate for the manufacturer of these kinds of devices to understand how their products are being used. And then once you think about the scale of use of these physical things in the physical world and how you're going to go and manage them, especially in a commercial environment, then it actually becomes very interesting to go and take even simple things and instrument them. So let's take a lamp, not necessarily the lamp that I have here, but lamps that you might find in an office building. If you have a very large office building, it might be very interesting to understand which of the lamps are broken, and how long you have put a new light bulb in, you replace it, whatever that light bulb or light device, I don't even know how we call this in English. You put this in, and then you have a certain number of hours that this works, and you can go and just within your environment that you have with the particular electricity that you have, your light bulbs may last a particular time, and you can be preemptive and go and change them out, but you don't want to do that too early. So as you have a large office building that you're managing, even instrumenting something like a lamp, so you can figure out what is the energy consumption, what is the duration, what is the status, is it on or off, or is it broken, when did it break, and all kinds of things. That might be already something that's interesting to know, where the device per se, the lamp per se, is fairly dumb. We can go and do things that is on or off, but collecting further information might be interesting if you're doing that at scale, and you just can't look at every individual one, because you might not only have one building, but you might actually have a very large campus of many buildings, and you're going to go and manage them and want to make sure that nobody's in the dark, and you know those things. So there are legitimate reasons to even take the simplest devices and equip them like this. I take the toaster as an example for a device which is in the household, or in an environment which is also commercial. Obviously, when this toaster breaks, then that's a sad occurrence, and I will probably go to the electronics store or electrics store in the case of a toaster, or I will go and just order a new one online, and then it won't have toast for a day, and that's not going to kill me, and that's only going to mildly annoy me. But if I'm a hotel and I'm offering breakfast in the morning for 1,000 people, and I have a hotel toaster, if that thing breaks, people will be angry, rightfully so, because they can't get a proper toast. Once you get into the commercial environment, things change. So you might have a coffee maker, and if you have a coffee maker, a commercial coffee maker in your office building, you know that if those things ever break, you're getting close to a riot. People are very grumpy. So you have these kinds of devices in a commercial environment, and then having a way to predict when they're going to fail or avoid that they're failing altogether is going to be very interesting. So take the coffee maker, for instance. I don't have a coffee maker here. I didn't bring that down from the kitchen. But if you have a coffee maker and the manufacturer can actually know that a device in the current state of health and the current usage of the grinding mechanics, if that is likely to fail within the next, let's say, 2 weeks, the manufacturer or the authorized service center that you have a contract with can actually come out and proactively service the device so that it doesn't break. But for that to happen, you actually need to know. So what we're seeing is a trend that manufacturers or operators of devices, may that be lamps, may that be toasters, may that be laundry machines, may that be dishwashers, may that be vehicles, cars, trucks, trains, subsystems in those devices are starting to think about how they can go and connect these things to the internet, directly or indirectly, where you probably have a home automation system in the house, and we'll go and connect all your lamps, so you can go and turn your lamps in the house on or off completely, and you can go and control the entirety of your house through a gateway device you have in the house. So you have a thing that's probably not a general purpose computer. It's probably a home automation system that you can go and buy and that you can go and hook up your things to, which have some electronic switches that goes over the network over the power line that will allow you to go and control these switches that are sitting behind your dumb devices like these, and can turn them on or off, and you can go and have a home automation system which goes and controls them. And then you have a way to go and take that entirety of the home automation system and now hook it up to the network so that you can take your iPhone or your Android phone or your Windows phone or whatever other device you have, or you go on a website, and you can turn the lights on in your house if you're away, or you can reprogram things that are in your house when you're away. Maybe, it's all those things a little bit complicated, so you may want to help your spouse with that, with remote controlling, or just plainly you want to turn the house lights on or off when you're away, so that nobody comes in and steals your things because you're obviously out of the house, but you want to kind of create the impression that you're there. So there's a lot of legitimate reasons in the household and the commercial space, and also obviously in industrial spaces, to go and get data from these devices, but also to control them, to have a flow back to regulate what they do. So for a toaster, that's not so likely, but if you have let's say a coffee maker, and you have a very high quality coffee maker, you might even be able to go and adjust the grinding and mechanics in certain ways remotely, because you're being called and you say, the coffee's too strong. And so you may want to be able to go and service that. But certainly, once you think about vehicles, you have a vehicle, your car, you park in mall, you walk away from the vehicle, you're already 100 meters, 100 yards away from the car, and you're like, did I lock that vehicle? So do you want to go back? Yes, you might today. But if we're zooming forward in our wonderful lazy world, it's actually fairly attractive to go and just pull out your phone, pop the app open for your vehicle, and then see the status of your vehicle. Yep, the door's open, and then go and close it just by a click. That's something they can imagine being a very easy thing to do, but then we have to think about how do we actually do that connectivity between the devices. What's interesting, if you think about that space, if you think about automating these devices or just collecting data from them, and you think about lamps, you think about toasters, you think about dishwashers, you think about laundry machines, you think about anything you can have in the household, and then in commercial spaces, temperature sensors, humidity sensors, pollution sensors that are sitting in cities. You have all kinds of sensors that are around the places. Those will appear in vastly larger numbers than these general purpose computing devices. Also, what's interesting about that space is that if you actually need to have a control channel, right? As long as the device just tells you things, it's all peachy, because that's fairly easy to scale. Once you need to have a control channel, once you need to have a way to tell that toaster that there's a new firmware for that toaster. Once you need to tell that lamp to turn off remotely, once you need to tell a vehicle to go and lock the doors remotely, you need to have connectivity that allows you to actually reach back into that device and do something. And now you're changing the entire scale story. This becomes now something that is much more complicated than the web is. Because the web is built for me sitting in front of a computer and me kind of driving information retrieval by interacting with the PC. Here, in these cases, when I just want to unlock my car, now I need to have a way for me, through a phone, kind of driving a service that I can go and contact. That's where my app connects to. And that service now needs to be able to go and talk back to that vehicle, but it needs to do that through some established traffic route. And so that traffic route is to that particular vehicle. And if you're selling vehicles, you're selling hundreds of thousands of them, or tens of thousands, hundreds of thousands of them. So now you need to maintain these routes in parallel. What's interesting about this, as I talk to customers who are interested in doing those things, is that's a scale challenge, which kind of is, which turns out to be fairly overwhelming for a lot of people. If you're building a website, even for a large audience, you deal with let's say you have 5 million people who are registered on your website, which is fairly successful. Out of 5 million people, even if you have a fairly successful website, only a few thousand will be there concurrently. If you have a website which actually has a lot of draw with people staying for a very long time, like Facebook, we might go higher. But an average site where people scroll by once a day, that would be high, or just a few times a week. You don't have as many concurrent connections on your service. If you are an internet enabling devices that take commands, all the devices you ship maintain a connection into your service. So you're dealing with a challenge of a few thousand on the website towards probably potentially hundreds of thousands on the Internet of Things thing. And what we see is that then manufacturers who've so far only focused on singular things that they go and make, put into a box, ship out, and effectively forget for getting the money for it, are now faced with, they want to do this, but it's really difficult for them to scale it, and to think about the scale of these things, because they're now kind of pushed into a model where they need to go and scale higher up internet traffic than the folks who have been in that business for a long time, have been in the internet business for a long time, and know how to build websites. And these folks who are building those devices are now faced with a problem that's probably 10 times, sometimes 100 times more complicated from a scale perspective than that of websites and HTTP. So I want to go and talk about some of those aspects on the whiteboard and kind of lay out what that scale challenge is, and some ways of how people address that, and how messaging can actually go and help with that. So first I'm going to take a look at some patterns and explain the patterns to you, and then talk about some connectivity options that we might have to those devices. So what I'm going to start with is a lamp. Here you see just the bulb, so let's assume that there's some kind of lamp around this. You see this is perfect industrial design, and there's some kind of control logic on the side of that lamp, and I can talk to it. And just take that as an example of a device you might have somewhere. That device now talks to some service, and that service is collecting information. It's kind of being the control system for the device, and also collects information from that device. And that might be local, so it might be some device that sits close to in the home. But if you think about the lamp being out on the street, that might also be kind of at the municipal level, and that link between that lamp and that service might actually be public internet. So this might be using the municipal wireless LAN. Many cities in the US are getting that now. So this might be connected really through public ISP space with that service. And if you think this further, this may be a service that's sitting on a computer in the city hall, but may just as well be a service that sits somewhere in the cloud and does that. So if you think about the various different combinations between, where a lamp might talk to, it might talk to something that's in the house, but if it's a lamp that's out on the street, it might just as well talk to a cloud system very directly. There are 4 patterns for communication that occur here in the devices space. In the general purpose computing device space, where you have a phone or a tablet or a notebook, typically the traffic is initiated by the user ultimately. So you go to a web page and you're asking something, you're asking for information, you're browsing information, which means this general request response pattern that you have and very well supported by HTTP is the far predominant one. Once we talk about devices, which are not about information retrieval on behalf of a human being, it's not necessarily the same kinds of patterns. So I have so far identified 4 patterns, and I'm almost thinking it's an exhaustive set. So the first one is telemetry. So I'm going to kind of note that here is telemetry. Telemetry is all data that is being emitted by a device for consumption by some other third party, and it's being sent kind of in a one-way fashion, and the device doesn't expect anything back for this. It's effectively just the status of that lamp. What kind of data could that device have that it spews out? Well, probably on a schedule, every X minutes, we'll go and send its status, on or off, the number of hours that the light bulb has already been in service. It might send the temperature if it's on. It might send the data about the lamp per se, or it might not. We'll have other ways to get at that in a moment. So we'll send some status information down to the service. So that's telemetry. Telemetry is emitting information. If you think about other devices, if you think about a vehicle that may send velocity, position, and other things. Telemetry is all information that's being sent one way for consumption by someone else. The next is what I call inquiries. An inquiry is a request that goes to the service and causes a response from the service. But an inquiry is not necessarily request response per se, so that's inquiry. But it also may trigger a service to tell the device something on an ongoing basis. From a LAN perspective, I have some hard time finding a good case for a LAN where it might want to do an inquiry. But let's go back to the toaster example that we had. The toaster, let's say you have a fancy toaster, and the toaster can go and toast the weather conditions onto your toast. So a sun and a cloud and a snowflake and the temperature of the day. That would be awesome. So you know whether you appropriately dress as you're buttering your slice of bread. Well, the toaster doesn't know about the weather, so it would have to go and inquire what the weather conditions are. If you have a car, the car has a route that it's planning, so the car might want to inquire about traffic status or special problems on that particular route. So it may do an ongoing inquiry for this. Or the lamp might go and inquire, now I have an idea, what its allowed energy consumption level is if you manage that centrally. So the lamp turns on, and the lamp, you set a energy consumption level across all of your devices, and so it can only use so much energy, and it will go and acquire as it turns on, so it can regulate itself to the necessary energy consumption level, and then it could, it might be a little dimmer than usual. But that's something that might be an inquiry. And as that changes from the management side, you can continue answering that inquiry. So this is a message that is being sent one way. And this is a two-way response. But it might be one message that's being sent down matched by one message that's sent up, but it could also be one message that's sent down and matched by n messages that flow back up. The third pattern is coming from the server side. The third pattern are commands. So you send a command, so that goes first, and then you get an acknowledgement or status of execution back. So the service tells the lamp to go on or off. That's if you have a control system in the house, that's a logical thing. You can actually centrally control all the lamps. If you're thinking about that at the municipal level, you have a street and you want to turn all the lights in that street on or off. They can go and tell that lamp to do that on by itself. Or you send it some other command. You ask the device something, so you ask the device for what's the lamp that's installed, or what's the light bulb that's installed, or what is your status, or are you healthy? So you can go and do a command, and the device kind of gives you information back. And that again is a one request that might be matched by one response, or might be having n multiple responses, or a continuous string of responses, which I call solicit push, so that you solicit further pushes of data in that direction, and then you can also kind of unsolicit them by sending a further control message, which then is going to stop the flow. And then the fourth pattern, so let's go and write this down. So the third one is commands, and the fourth one is notifications. And notifications are environmental information that's being given to the device that is outside the scope of that device. So the device doesn't know about this, but it's important for its operation. So I was talking about the energy level. If we want to go and effectively cut the energy level across like a municipal grid, if we want to go and inform devices, field deployed devices about something that's going to happen. Let's say you have instead of lamps, you have wind generators, and you want to tell the wind generators of upcoming weather conditions. They don't know what the weather report is, but you can tell them. And so notifications are effectively like the telemetry piece, but they're the other way around. So it's one-way information that's being sent to devices to notify them of environmental conditions. So these are the four patterns. The interesting part here is, and one of the interesting challenges, there's two interesting challenges here. One of them is that this traffic here is service initiated. And it might be service initiated at any point in time. So these pieces are fairly easy. If the device is somewhere deployed in the field, and it sits, and the connectivity is, it could be 3G, it could be Wi-Fi, it could be some other model of connectivity. This device will typically sit somewhere behind, naturally sitting somewhere behind a NAT, and not be directly exposed to the internet. It will if it's sitting on the 3G network or UMTS in Europe, or some other carrier network, it will be on that carrier network. If it sits on Wi-Fi in a house, it will also be sitting behind that NAT. So the device itself will not be directly addressable, but it will, through normal means of connectivity, as those devices get data access through those networks, it will be able to make calls out because it sits behind a NAT, and we'll be able to talk to a service if that service is exposed through the internet. So these two patterns, the first two, are fairly easy, and for telemetry and inquiries, the normal internet model and HTTP are actually a good fit if, and only if, they don't produce too much overhead over 3G, over those cellular networks. When you think about cost in terms of cellular networks, there's a lot of penny pinching going on because often the data that's being sent by these devices, if this device sends a status and it's a lamp, the status might be all of 3 bytes, and doing an HTTP post with a security token and all the things that are involved there might be easily 3, 4K. And so if you have a payload of 3, 4, 5 bytes, and you have an overhead of 4 or 5 kilobytes per request, that's enormous. So therefore, there are a number of protocols, AMQP being one of them. Is a connection-oriented protocol, MQTT specifically for sensor technology, and a number of other additional protocols which are much more suitable for that kind of telemetry traffic than plain HTTP. But for these inquiries here, that's the classic HTTP pattern for that. HTTP is also certainly a candidate. Where it gets more dicey is when the traffic is service initiated, because here the device now kind of needs to listen for traffic, needs to be ready to listen for traffic, and that's more difficult because now the device is assumed to be on a network where it's not immediately addressable. So that's a harder problem to solve, and folks are coming up with interesting ideas around that one. The first possible idea is, of course, to go and make this, use the web technology for this and make it an HTTP connection. So use HTTP not only for the first two patterns, but also for the second patterns. And what that means is effectively that the device will have to go and start soliciting messages. So it will go and have to go and park a request at the service and wait for messages to come up, and then pull the messages out. It's called long polling. The problem with long polling here in that scenario is that it's a very busy model. We have to assume that these devices come through some sort of proxies and that this service is load balanced. And because HTTP is not able to multiplex over its socket, you need to keep that socket entertained so that any of these intermediaries are actually not discarding the socket. So that requires that you have traffic going about every 60 seconds. So when you have this long polling traffic, you basically just go and pull data up. That is very busy, but that load is mostly on the service. The biggest issue with that is it first of all causes a lot of traffic over 3G and metered networks. And if you have hundreds of thousands of these devices in the field, and you actually have to get a SIM chip for each one of them, you can go and negotiate. You can go to your telco and you can negotiate some good rates. If you are very, very cost conscious in terms of the data that you're flowing around, and if every request costs you a few kilobytes and you have to do that every minute, then you're going to be using very, very much data. The way you can deal with that is you can do fewer requests, but then your latency is going to be higher because you're going to have stuff waiting here, and you have to kind of wait for the next train to come down to pull that up again. Also, if the device runs on battery, all that extra traffic will cause the 3G chip to be always active, and that's a very power consuming thing. What you would rather want to do is you want to stay on low power with a normal baseline GSM signal, and as soon as traffic comes kind of towards the device, you want to wake up and then turn that chip back on. But if you pull every 60 seconds, then you never get into that situation where you can actually go and do that. So HTTP, for that path, is not an ideal choice. The other thing that people do is to change the network, to turn the story around so that not only this is a service, but now people are being clever and they say, well, this is a service too. So instead of just making the service listen, they also now make the device listen. For that, you now need to have two things. First of all, you need to be able to make the device immediately addressable, right? And you also need to have a way to go and secure that link. So what's happening is, and that's what we see fairly frequently now, is that folks are doing the following thing. Let me just take the patterns away. And what they're doing is they will create a VPN. Actually, that's not the right way of doing this, of showing this, but kind of, that's probably the right way of doing this. So it's a VPN. The service is kind of mapped into the VPN. There's a VPN gateway that's sitting here. And so the VPN gateway creates that secure space, that isolated space that is that private network. And the device now sits still on the public internet, still sits on public internet space. And so what the device now does is it creates a connection into that gateway, and that gateway now maps that device kind of into this VPN space and gives it effectively an address. So you have a secure tunnel, so that's secured by transport level security or by IPsec. A tunnel that goes from the device through the VPN gateway into this space here, and that's your private network space. In that private network space, you run services, extra services on the side, that now allow you to treat this device like in any private network space. So you have DHCP, and you also have DNS. So the device shows up, asks for DHCP, because the nice thing is this is all layer 2, link layer, let's say link layer connectivity. The device shows up, gets a DHCP address, so it gets 10.1.20.20. That's the device now. Probably registers with DNS as well, and now it's addressable from that service. So that's beautiful. It's an absolutely beautiful model to go and create that connectivity. But there is a catch. VPN is often equated with being a secure, creating secure network spaces, which it arguably doesn't. What we have here is now a way how we have a link layer connectivity plane between the device that you have here and the service that you have here. Maybe even if the service is routed, you still have link layer connectivity. Now let's go and add another device here. So, or here. So we're adding kind of additional devices in here which are sitting somewhere else. These devices might be owned by someone else, they might be deployed somewhere else, they might be physically in a different place, and they might not be under your direct control. If I now go and crack this device open, so I actually gain physical access to this device, I now have a device which can automatically, as it turns on, join this link layer network and be on the same link layer as all these other devices who are owned by someone else, which is quite a bit of a security thing. If you have a field deployed device that you don't have any physical access security on, and that you as the service operator don't immediately own, so if you sell a device, if you sell a toaster to a consumer, and that device can go and connect through a VPN into a link layer, kind of shared link layer space, where it's sharing that space with everybody else, you're now giving people who are hacking into those devices an avenue to go and talk to all those guys. So that's a bit of a risk. So what you'll have to do is you'll have to treat all these devices which are connected on that VPN space as if they are connected to the public internet directly. Because you have to assume that if anybody gains physical access to the device and gains physical access to this link and gains physical access to the key material that's required to access your VPN, then you have a breach in that entire system. Which in the end means that you need to take all those devices and treat them as if they are public internet facing. So you need to firewall them, and for any services that they expose, for any commands that they understand, for any notifications that they get, you must have complete access control on those devices directly, which makes that system fairly complicated. In addition, one thing you one trap you can't fall into is kind of one of the classic fallacies of distributed computing, and that is that this network is going to be stable and reliable. You will have to assume that the connectivity from these devices into that into that network, into that private space, not secure space, private space, is happening through 3G, Wi-Fi, and we also need to assume that these devices may be roving around, which means that the connectivity is not necessarily stable, and it certainly is, because you're going through public space, it's certainly subject to congestion and certainly subject to outages. So if you're doing that dance, if you're treating this like a classic IP model or internal LAN model, you also need to make this model stable in the face of disconnects, and those disconnects can be fairly frequent. If you have a device and that device is in a vehicle and you're driving around, then you might be disconnected very frequently. So you need to make this address probably stable, and you also need to have a way for, well, to do something when the device is currently not available. So let's say you have, let's assume you have this device and the device has that address. So now it's currently out of reach, and it's driving through a long tunnel. What do you do here? How do you send a command? How do you send a notification to that device? Are you waiting for a minute, 3 minutes, 4 minutes? How long are you going to wait until you give up on sending that notification to the device? So treating this model, treating the devices as if they were just normal internet servers, is certainly, like normal web servers effectively, is certainly possible using a VPN, but comes with a whole set of side effects and problems. VPN is not a secure space. VPN creates a private network with secure tunnel into that private network, but that private network itself is not a secured space. Which means if you let untrusted parties into that private space, and those parties either don't trust you, you don't trust them, or they don't trust each other, you have to defend everybody from everybody. And that needs to be clear. Also, you need to deal with bridging or dealing with connectivity issues and sparse connectivity, and what happens when the system is not available. So these are hard problems if you're building systems, and certainly also building systems at scale, because these VPN gateways also have a limited capacity, which means you don't only need one, you will actually need very many of them if you have a sizable number of devices. The largest you can buy here of that sort hosts like 10,000, maybe up to 50,000 VPN connections concurrently. But if you have more devices, you have to go and scale this all out, and then you have to go and load balance this, and then it gets actually kind of tricky to go. If you get disconnected, you have to go and pin yourself to a particular VPN. So this gets very complicated. You can do it that way if you can deal with the security repercussions, and you can do it that way if you actually have a way to go and solve the problem of sparse connectivity. There is a completely different approach to this, which is actually making this fairly straightforward. The other approach you can take to create addressability is to have the device have an agent that acts on its behalf in terms of message receipts. And then the device comes and picks the data up. You can make a mailbox. One way to make a mailbox is to have a queue. And one way to go and take the data in from the device in a secure fashion is to have another queue. So you have an ingress queue and an egress queue. The nice thing of using queuing for this is that, first of all, on the way down, as you're accepting telemetry or you're getting inquiries, your service can never be overstressed. So if you have all these devices in the field and you have tens of thousands or hundreds of thousands of them, they might go and ask you for things, or might send telemetry in big bursts, like every time on the hour, or if you have vehicles and they're all sitting in traffic. So there's situations where you get kind of naturally bursting traffic out of all kinds of situations. If you have that, putting that into a queue and having the queue run high is actually certainly preferable over overstressing your service. So instead of pushing that traffic straight through into your service for processing, it actually makes a lot of sense to go and have the service pull that data off a queue. So the queuing layer will give you a layer of defense that will allow you to go and deal with that ingress better. Second, for egress, if you want to go and address the device, having a queue that's assigned to the device, where effectively the queue is reserved for the device and kind of is assigned to the ID of the device, is a clearly superior model for direct connectivity, or for establishing the connectivity. If instead of sending data to the device and trying to solve that addressability problem with the VPN and all the repercussions of it, you go and send from the service to the queue any commands or any notifications that you want. The device will go and create a connection to that queue, and it will create that as a long-lived socket connection over a bidirectional protocol such as AMQP, which gives you now a way to go and create a link where you are you're soliciting messages. You can actually, in AMQP, you have a credit-based model, which means you can ask for 10,000 messages or 100,000 messages, and as long as your credits are not used up, they're continue to be serviced. And you walk to that queue, and that queue, if that's publicly addressable, you always have a place to come back to. So you have the addressability solved by having an intermediary, which has a fixed address in public internet space you can send to, and you also can pick up from. That device can now roam in any public network as long as it can't see the internet, and it always has a route to that queue. So even if that connection gets cut, the only thing you have to do is reestablish that link and go back to your queue, and that's your mailbox where the data shows up. So using messaging solves the addressability problem that in VPN you're solving with DHCP and DNS very, very nicely. And it also solves the sparse connectivity problem of being occasionally disconnected. In addition, because you have the queues in the middle, you also solve the problem of having bursty traffic from the bottom, and also having bursty traffic from below, where you might want to send a number of bursty notifications that the device can't process because it's on a very slow network, but you won't lose that data because you have a mailbox that's sitting there. Well, in reality, you will likely not have a dedicated queue per device, but rather have the model in a little bit cleverer way and use a pub subsystem for this, where you have what's called a topic, and each device has a subscription, and that subscription carries a set of rules with it. The rule here might say, I want to accept the message into the subscription for that device if the ID is 1, 2, 3, 4. Or if the group ID is 4. So you can group those devices by whatever criteria one, so I'm just making this up, the group ID. And so you can go and say group ID, or you can say if this is in a building, the building ID 10, or you have the street ID, what that is 40. Whatever you want to do in terms of addressability, you can do that with that subscription, and now you can hang, off that topic a great number of subscriptions, each being a bucket for any individual device. But you can send one message in, and if that's fitting the rule for, let's say, an entire street, then every device on that street, everything that kind of fulfills that rule, will actually be getting that device. So using PubSub for that addressability is a wonderful thing. For ingress, likewise, you might not only have a service, but you actually may want to go and take that telemetry and store it. So again, you have a topic here, you have a subscription. The subscription here assigns that to the service, but you might also want to go and take the raw events that you're getting in here. You have another subscription, and that bleeds that off straight to storage. So there's an article that I wrote about this. It was in MSDN magazine in June 2012, which kind of tells that story. So the link is down below in the script. I also have the alias, the shorthand address right here, so you can go to it. And there's a follow-on article to this. The articles are a year old. So what they don't address yet is the AMQP piece, and how we can actually, we're now working with the Apache Foundation, who has a wonderful project, Proton, part of the Cupid project, who are building a C-based client, very suitable for small devices, which can talk directly and is tested against the AMQP endpoints on the Surface Bus, and can effectively trade this link, the feedback link, back into the devices in a wonderful fashion. The nice thing about using messaging for this is all the things that I said, but also keep that in mind that the device here doesn't need to be on the public internet. It's not exposed either on the internet, because it's coming through third-party infrastructure likely, and it's also not exposed to the risks of sitting inside a VPN and kind of having link-level integration with untrusted parties, because it's always coming through that level, and it's always the integration that's happening here is always at the application level, which means this can be very easily secured through standard mechanisms, TLS. There's no magic, there's no proprietary protocol. It's actually fairly straightforward. So we're working with a number of customers. If you find that interesting, if you recognize that problem in your own environments, feel free to write me an email directly, clemensv@microsoft.com. I'd be glad to talk to you, and we're actually working with a number of customers directly from the product group to solve those problems, and certainly we're interested in the hardest challenges. So if you have hundreds of thousands of things that you want to go and connect, where you want to have, pay attention to the individual thing, but also pay attention to groups, do groupcast, unicast, you want to go and control things, and also collect telemetry and collect it either into the cloud or also collect that through the cloud into your own data centers, then we're certainly willing and very interested in helping you with that. So much for this episode. I'm going to follow this up. I'm actually, the article that I'm referring to, I'm going to go and go through that in more detail, through the patterns in one of the following episodes after this. So until this, thank you very much for listening, and I'll see you next time.